This lecture focuses on one-dimensional potential. But before heading directly to one-dimensional potential, let us discuss the various configurations in which a particle can exist under a potential field. So the first configuration is a bound state. The particle can exist in a bound state under a potential field. A bound state is a state in which the motion of the particle is constrained spatially. That is, the particle cannot escape to infinity. As can be seen from the figure, a particle with energy E1 is bound in the classical turning points x1 and x2. It cannot escape to infinity. Whereas the particle with energy E2 can escape to infinity in one direction and is bound in the other. So this is not a bound system. But there is an important theorem in one dimension that there are no degenerate bound states. Here's a small proof for this theorem. But we have to initially assume that there are two wave functions psi1x and psi2x are degenerate with energy eigenvalue E. Here's a list of proceeding steps. What we have obtained is psi2 is nothing different but is a constant multiplied psi1, which implies that there is no degeneracy in one dimension for a bound system because they are not different, it's the same function. Unbound states. As can be seen in the figure, the particle with energy E is bound in one direction and unbound in other. That is, the particle can move between x is equals to x1 and x approaching minus infinity, and the energy spectrum is continuous. Next is an infinite square well. The potential is listed here, but the important thing to note is the wave function is 0 for x less than 0 and x greater than a. Why is this so? The reason is because the walls are at infinite potential, which implies that the uncertainty of energy outside the well is also infinity, which indicates that the uncertainty in the momentum of the particles is infinity. So from uncertainty relation, the uncertainty in the momentum of the particle outside the well is 0, which shows that the probability of finding the particle outside the well is 0. So we are only left with a wave function inside the well. So there is a Schrodinger equation for it, and the wave function comes out as a sin kx plus b cos kx, a and b being constants. Using the boundary conditions, the constant b is eliminated and the wave function is a sin n pi x by a. As can be seen, the energy is quantized, and here is 1 2 3 4. Okay, what is a? How do we get it, the value of a? We need to normalize a to get the value of a. We need to normalize the wave function to get the value of a. And what is normalization? Normalization is minus infinity to infinity integration of sin star x sin x dx equals to 1. Why do we need to normalize a wave function? Because what has meaning is a probability or probability density. Wave function has no meaning, so only probability density is what is of our importance. So we need to normalize our wave function so that the probability of finding the particle in a particular width or in a particular range is finite. It should not exceed 1, which imparts meaningless definition to probability. So we need to normalize the wave function to render definition for probability. The total wave function is given as this. The factor e to the power minus I e n t by h cut is a time dependent Schrodinger equation solution. The figure shows x from 0 to a, the wave function in the potential well. Black represents the probability density with respect to x, brown represents the wave function with respect to x. The probability density amplitude is double of the wave function. But what is of importance is the ground state wave function is symmetric and the first excited state is asymmetric. This is because the potential is a symmetric one. So the potential, or rather Hamiltonian, commutes with the parity operator, and when two operator commutes, then the eigenfunction of parity operator is also an eigenfunction of the Hamiltonian of the system, and the eigenfunction of a parity operator are of definite parity, that is either even or odd. So therefore the wave functions have either odd or even parities. Now what is important is psi n x is an eigenfunction of energy, but it's not an eigenfunction of momentum. So we need to devise a method to get the eigenfunctions of momentum operator, which is shown here. The average momentum is also 0. But why n is equals to 0 state is not allowed? N is equals to 0 implies 0 energy of the particle in the ground state, which implies the particle is at rest. But 0 energy is also the momentum is 0. So the two conditions violates uncertainty principle. So in order to have a hold of uncertainty principle, we need to avoid this condition, and the ground state is n is equals to 1, which is also called the 0 point energy. Next is a finite potential well. That is, the walls have a finite potential. Now since the potential is finite, so the uncertainty in energy outside the well is finite. The momentum is also finite, which implies the uncertainty in the position of the particle outside the well is also finite. So now we have to devise three Schrodinger equations for the three different regions. Here I have eliminated the coefficients with constant b and constant e in order to have finite wave function at x is equals to plus minus infinity. The plot of wave function psi of x in red with respect to x and probability density psi mod of psi x square with respect to x is shown. It can be clearly seen that the wave function is existing outside the potential well. That is because we have a finite probability of finding the particle outside the well. Now what is important is the lambda that fits in the well are longer for an infinite, they are longer than an infinite square well. So the momentum of the particle is less. So that means for a given n, the energy levels are lower in a finite square well than an infinite square well with the same value of n. We have to keep in mind when we are drawing these wave functions that at the boundaries, that is at x is equals to 0 and x is equals to a, the wave function and its derivative is supposed to be continuous. Next is symmetric infinite square well. I am not going into the details of writing Schrodinger equation, but what is of critical importance here is the form of the wave functions. So the wave function has different forms for different quantum numbers. That is, the ground state is cos, the first excited state is sine. Now why is this so? It's just to satisfy boundary conditions, but because we want our wave functions to vanish at x is equals to a by 2 and x is equals to minus a by 2, that is, the wave function should be 0. So for the ground state, that is n is equals to 1, the cos n by x by a is 0 at the boundaries. But for n is equals to 2, which is the first excited state, we need nodes at x is equals to minus a by 2 and x is equals to a by 2, but also at x is equals to 0. So thus wave function psi n by x by a satisfies the condition for the first excited state. So we have two different solutions, set of solutions for the different states in a symmetric infinite square well. So this is it. For any queries or remarks, you can contact me at prabodhan.physics@gmail.com. You're most welcome with any remarks or negative suggestions. Thank you.